All right, thanks, Mark. So, right, so I wanted to say a few words about three-manifold groups. So by this I mean, so I want to discuss some topics about some open questions and properties of three-manifold fundamental groups. And here, the general case is sort of wide open, so I'll be restricting to the finally generated case. So there's the fundamental groups of for compact three manifolds. Or finally generated fundamental groups. So it's a classic fact that if a three manifold has finally generated fundamental groups, then it's actually finally presented and it's the fundamental group of a compact manifold, possibly with boundary. So the infinite generator case is in general fairly wide open, so I have nothing to say about that. But anyway, so the topics I wanted to discuss today were first, I guess what can be called profinite rigidity. And this is roughly, can three manifold groups be distinguished by their finite quotients? So this is in some sense a classic topic in three-manifold topology. The way that you learn to distinguish knots from the unknot, for example, is via colorings, which is really just encoding dihedral representations. And so if you generalize that question, then this is sort of the natural generalization. A second topic I'll briefly discuss is orderability. Can a three-manifold group act on R by orientation preserving homeos? I should say faithful. So, and if so, how can we tell? And then the third property, which I probably won't have time to get to, but I'll maybe hopefully say a few words about, is PD3 groups. So do closed three-manifold groups have admit a cohomological characterization? So so these topics are by no means exhaustive, but I guess I chose some things that maybe are of interest to members in the special program this year, and which might be topics that are accessible by, or at least which current techniques sort of have something to say about. So just a remark. If you're interested in more about these topics, there's an exhaustive survey by Aschenbrenner, Friedel, and Wilton. That's sort of a pretty good kind of encyclopedic reference on this sort of topic. So if you want to find out more about these sorts of things, I would suggest looking there. And I think it just appeared as a memoir. Okay, well, so to say something about these, I first need to explain something about geometrization. And I should say also that in three-manifold topology, sort of talking about the group and talking about the manifold are almost indistinguishable. So in 3 dimensions, the fundamental group nearly uniquely determines the manifold, and so they're both aspects are of interest in studying three manifolds, and somehow three-manifold topologists have been forced to learn a lot of group theory over the course of time because of that. And they're also a very special class of groups. So there's properties of three-dimensional manifold groups that absolutely don't hold in for fundamental groups of four manifolds, because you can realize any finally presented group and it's way too wild in 4 dimensions to say anything sort of universal. Okay, so so geometrization, I'll review that briefly. So let M be a closed, orientable three-manifold. Here, actually, the orientable hypothesis might seem kind of not very important, but in fact, actually, no one's actually written down a version of the geometrization theorem in general for non-orientable three-manifolds, which is kind of maybe a little shocking, but I guess it should be possible, but someone hasn't sort of gone through and made sure everything works, I guess. Okay, so for closed manifolds, there exists a prime decomposition theorem. So M will be homeomorphic to a connect sum of some number of manifolds where the mi are prime, meaning that they're not a non-trivial connect sum. Any connect sum n would have to be a 3-sphere. And so the existence of such a prime decomposition is due to Kneser, and the uniqueness is due to Milner. So by uniqueness, I mean the factors are unique up to permutation and homeomorphism. Again, here, orientability is essential for making sense of the notion of a connect sum, because you need an orientation to determine how to connect two things together. So by connect sum, I mean you take two manifolds like M1 and M2, you remove little 3 balls from them, and then you glue the corresponding 2 spheres together. And so the orientation tells you which gluing to choose, and it only matters up to isotopy. So, okay, so what happens in the fundamental group there? Well, pi 1m then is equal to pi 1 m1 free product with pi 1 mk. And here there's a kind of uniqueness theorem as well, due to Grushko. So here you get sort of a unique set of factors plus a free factor. In the three-manifold case, the free factors will come from connect sums of S2 cross S1s, which are the three manifolds with Z fundamental group. But of course, you can act on the automorphisms of a free group and get lots of different ways of identifying them, and so that's built into Grushko's theorem. So actually, you get in some sense, the proof of geometrization and Grushko's theorem gives you a new proof of this Kneser decomposition, but not a very direct one, because it also involves the Poincare conjecture to see the finiteness part. Okay, so then to state the geometrization theorem of Perelman. So again, this was announced by in preprints by Perelman in 2003, but it took many years for people to write down sort of complete proofs. But it's pretty well accepted now. So I won't write down all the many people that contributed to absorbing this result or disseminating it. But anyways, for M prime now, enclosed, there exists, actually, sorry, let me say here irreducible. Irreducible just means that if you're prime but not irreducible, then you have to be S2 cross S1 essentially. So just rolling out that. Then there exists a surface inside of M, unique up to isotopy, where the components of sigma are tori and Klein bottles, and they're pi1 injective. And the complementary pieces, if I remove sigma from the manifold, these emit geometric structures. So these are modeled on the Thurston's famous 8 geometries. So and sigma, the uniqueness is also, you have to assume that sigma is minimal with respect to this property. So in the case, if sigma is non-empty, actually there's just 2 geometries that appear. So there's the geometries are H3 and H2 cross R. So the H2 cross R geometries come from taking a mapping torus of a finite order of a compact surface with boundary. So these guys are always fibered. So you take a surface maybe with boundary, cross it with an interval, and you glue it top to bottom by some map that has finite order. And so if you put it, you can put it, the meaning of the geometry here is if I take put a hyperbolic structure on this surface, which is invariant by the finite order, then I can induce a hyperbolic structure on the mapping torus. So in here, I guess I should have said that chi of sigma is less than 0 here if we take a surface sigma. Oh, and I should call this something else. Sorry about that. Let's say pi. The hyperbolic 2-plane.
Yeah.
So
Will be this surface, not H2.
yeah, so this is a quotient of H2. It's a compact Riemann surface with negative Euler characteristic. And then it's universal cover, or rather it's interior. I mean, really I should remove the boundary because I took the complement of a compact set, so it's non-compact. But the interior admits a complete metric modeled on H2 cross R. And so the universal cover will map naturally. There's like H2 crossed with R, and it maps onto here. Well, you have the covering translations are the surface group, and then translations in the R direction.
So when you say this geometry, you mean that the universal cover has this geometry?
That's right. Yeah. So I didn't define what a geometry is. So a geometry in the sense of Thurston is you have a a group of diffeomorphisms of some manifold, and you choose an atlas of charts in your manifold where the overlaps between the charts are restrictions of these diffeomorphisms. And so here, the diffeomorphisms allowed are precisely the isometries of H2 crossed with the isometries of R. And so if I take, this has a geometry modeled on that, and that there's an atlas of charts that are modeled on those isometries. So H3 geometry is, you take the hyperbolic 3 space with its group isometries of hyperbolic 3 space, PSL2C essentially, for the orientation preserving ones, and you look at a model atlas of charts based with that group. And here I should also say complete, so to get something non-trivial. Is there any other questions? Yeah. Okay. Okay, so if the surface is empty, then the entire manifold admits a geometric structure, and then there's a finite list that can occur there. So there's the three-sphere geometry, the Euclidean geometry, E3, SL2R tilde geometry, Sol geometry, S2 cross R, and nil geometry. And then, of course, in these two as well. So up to finite index, well, I said this H2 times R geometry, these guys are all fibering over the circle with monodromy, a finite order map. So what about these other geometries? Well, it turns out that the E3, the nil, and the Sol geometries are also, again, up to finite index. They're in Sol geometries up to finite covers are they fiber over the circle with torus fiber. Well, the S2 cross R geometry, well, there's only a few manifolds you have here, and they're, again, also virtually fiber over the circle with fiber a two-sphere. The case of S3 and SL2R tilde geometries, these up to finite index, these fiber over a two orbifold with S1 fiber. I haven't explained what an orbifold is, but again, up to finite index, it's really a circle bundle over a surface. So for the three sphere, that's really just a Hopf fibration. What about H3? So we've shown that all these other geometries fiber in some way or another. So the theorem that I proved, I'll attribute it to Wise as well, that finite volume hyperbolic three manifolds have a finite sheet of cover which fibers over S1. So here, Wise proved the case of non-compact hyperbolic three manifolds, and I did the case of closed manifolds. So the caveat here, though, is that it's not, the fibration is not in any way related to the geometry. It's just topological fibration. But the upshot of these results is saying that, oh, and I wanted to say a generalization of this. So this was a conjecture of Thurston, and So it's generalized by Shizitsky and Wise. No. No, I mean, in principle, it's computable. That's all we know right now. We don't have any kind of estimate of the index, unfortunately. In principle, I think you could go through all the proof and every step. I mean, it's sort of very complicated sequence of inductions, and the constants will keep getting worse and worse. And yeah, I don't even have a guess as to what index that would come out of the proof.
It should be bound by what?
I don't know.
Yes.
It's just by a computable function, let's say. That's all. Yeah, I don't have any guess actually. I mean, well, yeah, I won't venture to guess. Yeah. Yeah, computable function. Primitive. I don't even know about that. Yeah. Okay. Sorry. Yeah, I wouldn't guess. Okay, so Shizitsky and Wise showed that if M admits a non-positively curved metric, then M virtually fibers, and I didn't really define virtually, but let me just say, so there exists a cover, M tilde of M, finite cover, sheeted cover, with M tilde fibers over the circle. There's a nice characterization of fibering. So you get a map from pi 1 M tilde to pi 1 of S1, which is Z. So just purely in terms of the fundamental group, and the kernel of this map is finitely generated. So pi 1 of pi, if you like, surface. So finitely generated. And Stallings proved a nice converse there, that if you have a map of a three-manifold to group to Z, and the kernel is finally generated, then it's in the manifold fibers. So it's kind of a characterization in terms of the fundamental group. Yeah. Well, that gives you, yeah, certainly gives you a positive first Betty number, but still to get it fibered is still pretty complicated. Yeah. So yeah, Wise has this 180 or 90 page manuscript that is submitted somewhere. Some people. Yeah, it's still, yeah, even, yeah, getting for manifold to positive Betty number, getting them to be virtually fibered was still highly non-trivial. Oh yeah, sorry, complete non-positively curved metric. So I should say that, yeah, I'm skipping a lot of history here, but Bernhard Lieb characterized which three manifolds emit such a non-positively curved metric. So if there's a hyperbolic piece in the geometric decomposition, then there's always a non-positively curved metric. So in particular, it's generalizing this theorem. If you have any hyperbolic piece in there, then there's a finite cover that fibers. It's the non-hyperbolic case where you can have examples that that don't virtually fiber, and that was characterized by Svetlov. Characterized the non virtually fibered guys. It's actually an interesting thing that, well, comes out of this also, that these three manifolds have linear fundamental group. Actually it embeds into GL and Z for some n. And same with the machinery of Wise. You get an embedding in GL and Z. There's actually not, so the case of the manifolds that don't admit a non-positively curved metric, they're still not known to have linear fundamental group. So like if you take the mapping torus of a Dane twist, you take a, here's a mapping class where you take a surface and you cut out an annulus, and you glue it back in with by a shear that goes around 2 pi. That's a Dane twist. And you take the mapping torus of that. Does that have linear fundamental group or not? That's unknown. And I'll mention that my Yilu, my former student here, showed that in all the cases of graph manifolds that have a non-positive curve metric, they do have linear fundamental groups. So it's these remaining cases that are still open there. So that's an interesting property about 3 manifold groups that still is open. And in what classically was sort of the simplest, or the regarded as sort of the easiest case to work with, graph manifolds made with no hyperbolic pieces, and yet we still don't know this elementary question. Yeah, I would take a mapping torus of a Dane twist. So I take a Dane twist. So I glue it top to bottom. Yeah, I mean, I don't know how hard this is, but I'm just saying it's not in the literature. Yeah. Okay, so so the takeaway then is that we can get all 3 manifolds by taking mapping tori of surfaces and then maybe quotienting by finite group actions and then taking connect sums and gluing along tori or Klein bottles. That's sort of one way of getting compact closed 3 manifolds. Okay, so now I want to talk about residual finiteness. So the theorem of Hempel plus the geometrization is that finally generated 3 manifold groups are residually finite. So if you like, the intersection over all finite index subgroups is trivial, or any non-trivial element in the group, there's a homomorphism to a finite group where that element is sent non-trivially. So the basic question then is how much information is recorded in the finite quotients. More importantly, how do you extract? So, for example, if you have 2 3-manifold groups that have the same set of finite quotients, then are they isomorphic groups? So this is sort of the profinite rigidity question. If M1, M2 are, let's say G1, GI equals pi 1 MI, have the same finite quotients, then are they, is G1 isomorphic to G2? And again, we're restricting the 3 manifold because in general this is sort of well known not to be true. But actually, and I say profinite rigidity because if you know what the profinite completion is, then this is saying if the profinite completions are isomorphic, does that imply that the groups are isomorphic? The profinite completion, I might say a little bit more about that later, but the answer is no. So Funar gave examples of there exists all 3 manifolds with the same finite quotients. So we call these are mapping tori of these are mapping tori of tori, 2-dimensional tori. So the examples are roughly the mapping class, which is determined by its action on homology, are closely related. Like they have the same trace, for example, but they're not conjugate. And actually, there's some.
Several integer matrices which have the same trace but are not conjugate over the integers.
Yeah, over the integers, yeah. In the mapping class group, yeah. So yeah, two mapping tori, if the mapping classes are conjugate in the mapping class group, then the mapping tori will be homeomorphic. And that's essentially the converse if you restrict to the same fibering class, which in the solid manifold, there's a unique weight of fibers. So that's essentially true in that case. Well, up to reversal, I guess. Hempel found some simpler examples that are H2 times R geometry. So these are H2 times R manifolds. These are mapping tori then of periodic homeomorphisms of the surface. And there are two periodic homomorphisms, one which is the power of the other one. Then they'll have the same finite quotients. But the conjecture, though, is that if M is hyperbolic, M is determined by its by finite quotients. So this is a kind of profinite rigidity conjecture, at least for hyperbolic three manifolds. And here, these are all finitely generated fundamental groups of hyperbolic three manifolds, complete hyperbolic three manifolds. So, anyways, this virtual fibering result, gives some hope of approaching this sort of conjecture because you might expect, hope to have some kind of inductive argument. So, if you had two three manifolds with which are both hyperbolic, we know there's a cover of one that's fibered, and then you could try to prove that the corresponding cover of the other one is fibered, and in the same way, and that the two fiberings are equivalent to each other. So you can imagine some kind of inductive argument trying to induce up from surfaces or something like that. There's also
There was a question I meant to ask you. You said as a positive answer to this Magnus problem of whether you have an element it's decidable with an element in the group generated by some other finite set of elements.
that's right, yeah.
You said was true.
The generalized word problem?
Yeah.
Yeah, that's true for hyperbolic three manifolds.
It's not closely related. It's not connected with this problem.
No, it probably is. Yeah, it's.
But you can solve that.
Yeah, in a hyperbolic three manifold.
Yeah. That's
The generalized word problem, yeah. So one theorem or one corollary of is that hyperbolic three manifold groups are good. This is in the sense of Serre. I guess c'est bon en français. Mais, if you look at the map from G to its profinite completion, so the profinite completion is you take the diagonal embedding of G into all of its finite quotients, and then you take the closure inside of there, and so that's some compact topological group, and that's the profinite completion. And then if this acts on a finite module over the profinite completion, then H star of G hat M is isomorphic to H star of GM. I think I got that right. But what it's saying is that if you look at all finite index subgroups of G and look at the homology of those covering spaces, then that's determined by the homology of the profinite completion. And so So this is useful. At least it tells you you can distinguish closed three-manifold groups from non-compact three-manifold groups, because the non-compact ones will vanish in H upper 3. So you can tell that from the profinite completion. So recently, some progress was made on this profinite rigidity conjecture then by a couple of groups. So the theorem of Bridson and Reed, Almo Reed will be here in the spring, Boileau and Friedel from this year, is that the figure 8 knot group is distinguished by its finite quotients. From other three-manifold groups. And here I don't have to say hyperbolic three-manifolds, just any other three-manifolds. Of course, the figure 8 knot is the simplest hyperbolic knot, and so I'm taking the fundamental group of its complement. It actually fibers over the circle with fiber genus 1 surface, and so they sort of carry through the strategy that they can show any other three-manifold with isomorphic profinite completion would have to be a hyperbolic manifold with cusps, and then you can also show that it has to fiber with a circle, and then you can determine the monodromy from the action homology, which in the punctured torus case uniquely determines the monodromy. That's roughly, it's a little more complicated than that, but that's the idea.
Do they use the goodness?
Yeah, they're using goodness to rule out, it has to, well, to show there has to be cusp, it has to be a manifold boundary. I wanted to mention one other interesting conjecture that was discussed in a talk last week here at, might not be so well known. That's right. So the goodness was proved, yeah, I should have written down, I think by Grunewald and a couple of his collaborators, but I apologize, I don't remember the, right. So they proved that if you have an extension of a cyclic group by a surface group, then that's good, and it's preserved under finite incommensurability. So that's right. So there's an interesting conjecture. So here I'll take G is pi 1 m hyperbolic enclosed, let's say, like the Seifert-Weber dodecahedral space or something like that. And we'll take, say, lambda, a normal finite index subgroup of gamma, and let T1 of lambda equal the size of the torsion of H1 of lambda with Z coefficients. So this is really the, I'm thinking of it as you take a manifold, you take a finite sheeted covering space, regular covering space, you take H1 of that, and you just count the size of the torsion homology. T1 of lambda. Ignoring the infinite part. That's right, ignore the Betty number. Then the theorem that Tong Lei talked about last week is that the limb sup of lambda normal and gamma of the log of T1, the amount of torsion in lambda, divided by the index is less than or equal to the volume of M divided by 6 pi. And the conjecture is that, so this is conjectured by Lei and independently Bergeron and Venkatesh. It's conjecture that equality holds there. So Bergeron and Venkatesh are actually conjecturing it, say, for congruence subgroups in some sense. And so the idea here is that the torsion of the finite covers should be converging to the L2 Weidemeister torsion.
My memory is that paper had suggestion that if you were not congruent, the answer was different. Is that
Well, there does seem to be a different sort of growth for non-congruence manifolds. So maybe I should say, maybe they only conjecture for arithmetic ones, but yeah, I don't know whether, actually, I forgot to check whether they extended it. I think in discussions I've had with them, they believe it should hold in general, but I could be wrong about that. Anyways, Tong Lei conjectures it in general. So you would be able to extract, again, the homology of, torsion homology of this finite sheet of covers, you can extract from the profinite completion. And so in principle, you should be able to extract the volume from the profinite completion. Is sort of, and that would also be a long ways towards establishing this profinite rigidity conjecture, because any given volume, there's only finitely many hyperbolic manifolds with that fixed volume.
Okay, this young man's explained to me the difference. They're saying limit on congruence, but not the lim sub, which is what he's saying. But there are some sequences.
Right, so I'm just saying, I'm taking all of them. Yeah, okay.
Does he also conjecture that for appropriate covers like cofinal, the lim sup is a limit? Or is that wrapped up in a converse?
That's right. I just didn't want to state the general, the more precise conjectures, yeah.
Certainly true that the many numbers are growing more slowly.
Right, so the Betty number will grow smaller than the index by Luke's theorem, or maybe, I think it goes, yeah. Okay, so now I guess I have 15 minutes. I'll talk a little bit about ordering. Right, so I guess maybe I'll just say another motivation for understanding these profinite completions then is that, in principle, this would give us an algorithm to distinguish three manifolds. Not a very effective algorithm, but you would take two three manifolds and start writing down finite quotients, and eventually you come up with, one group that's a quotient of one but not the other one, or you could run it in parallel, subdividing triangulations and seeing if they match up somehow. And one of those two things would eventually succeed if you had this kind of profinite rigidity. Of course, it doesn't hold, in these special cases, but it might work sort of generically. Okay, so let me discuss briefly the ordering fundamental. I'll say a finitely generated group is orderable if it embeds in homeoplus of R. Well, this is really equivalent to saying that there's a left invariant order, an order that's left invariant by left multiplication. Equivalently, if there's a right invariant order, because you can do inverses. But so as an example, if we have a three manifold that has non-trivial first Betty number, so whose fundamental group has a surjection to Z, then pi 1m is orderable. So certainly you get a homomorphism of the group to homeoplus of R just factoring through Z, but that's not faithful. So there's argument of Boyer and Gordon, I think, and maybe Watson, that shows that, Boyer and Rolfson, that shows that you can actually get, use local indicability to get orderability here, so that you sort of, in between the cracks of Z, you fit sort of the orderings on the kernel, et cetera. But there's an interesting conjecture of Boyer, Gordon, and Watson. So here, M3 is closed and irreducible. Then pi 1m is orderable if and only if M is not an L space, if and only if M has a taut orientable foliation. And maybe I shouldn't attribute this part to them, but this is a dimension 2 foliation. So yeah, I don't have time to explain all the terminology. Yeah.
Why you would want that group to be
Orderable? Yeah, that's a good question.
I mean, can you use it for something?
Yeah, I don't exactly know the sort of origins of this. I mean, one nice thing about it is that you get this Kaplansky conjecture out of it, so that the group ring has no zero divisors. That's another conjecture that's interesting for three manifolds. It's discussed in the survey paper. You know, there's certain other properties of three manifolds that seem to be amenable to this Kaplansky conjecture. But
How do you see that if you embed into homeomorphism, you have a left invariance of the...
right. So you can totally order homeo plus of R just by you totally order the reals, and then you just sort of go through in order and see whether the two elements, does it map one above or below the other one. If they're equal, then you go to the next one, and that gives you a total order. It's sort of naive. So yeah, the fact that it's finally generated is special, though. So there's not finally generated groups that don't embed a homeo plus R just because their cardinality is too big, for example. Okay, so an L space, well, we're sort of in ground zero of the L space, or at least 1.5 miles away from it or so. This is sort of a Hegel-Fleur homology is as small as possible. It's the order of the torsion of the first of H1. And having a taut orientable foliation, this is a codimension 2 foliation. So you have, again, this is a geometric structure. So there's charts for the manifold that have a two-dimensional foliation. And so when you overlap two charts, the foliations match up. So you have a group of diffeomorphisms that preserve a foliation of the plane, and that's your model for the geometric structure. It's orientable means just that it's orientable, and then the taut means that there's a omega closed 2 form on M, which is non-vanishing on the leaves. So it's kind of a calibration. There's other ways to say tautness, that there's a closed loop that intersects every leaf, for example. And it was known by work of Ozath and Szabo, at least if you have a smooth taut orientable foliation, then that implies that the manifold's not an L space. But the converse is not known. So one interesting thing, if this conjecture were true, that it would give you a method for telling if the three manifold group is orderable, which we don't know why we care about that, but we don't know how to tell if a group is orderable. How do you prove that a group has an ordering? So we know how to tell if a group doesn't have an ordering. You just try to order larger and larger balls, and if it's not orderable, you'll get stuck at some point. You'll get some incompatibility in any order you try to put on there. So, but showing that something is orderable seems a lot harder. So that's maybe why this is an interesting question. There's another special case. If you have an orientable foliation, it might happen that when you pull it back to the universal cover, that it's actually totally ordered, and that the leaf space is just R. And then you immediately get an action on homeo plus of R. So that's a case where there's a correspondence. But anyways, this was recently proven for graph manifolds. So these are ones where the geometry, these irreducible manifolds, there's no H3 part of the geometry and the geometric decomposition. So all the pieces are modeled in H2 cross R, or it's one of the geometric ones that's not H3. And so this was by Liam Watson talked about this a couple weeks ago. So this was Watson, two Rasmussens, and a Hanselman. Okay. But they did this equivalence here. This equivalence was done by Boyer and Clay. The equivalence between top foliation and orderability. So there'll be talks about this at the workshop at the end in December here. And so while preparing this talk, I came across a question that I didn't know the answer to, and this might be an embarrassingly stupid question, but I'll state it anyways. If a three-manifold group is ordered, is its profinite completion? And here, here I just mean an abstract left ordering. Okay, this might be a stupid question, but certainly we know that any abelian torsion free group has a total ordering, actually bi-invariant ordering. But I didn't even know that this is true for like the free group. So that might be the first case that one might consider. Okay, so let's see. I have 10 minutes left, I guess. So I'll talk a little bit about PD3 groups then. Is there any questions? But I guess the upshot of this talk is supposed to indicate how geometry gets involved with the fundamental group, and the information can flow both directions. And what we kind of want to do in three manifolds now is make connections between these different geometries, which is kind of one interesting thing here. Here, Floer homology is also related to contact structures, and we want to see how those are related to properties of the fundamental group. Okay, so PD3 groups. So as I said at the beginning, the question is there a cohomological characterization of three-manifold groups, closed three-manifold groups? So, so an n-dimensional Poincare duality group gamma. So gamma is an n-dimensional Poincare duality group if for an arbitrary Z gamma module A, the cohomology with coefficients in A is isomorphic to homology HM minus I homology of gamma with coefficients in A. So this is also noted as gamma is PDN. So group theorists like to give sort of abbreviations to names of their properties because they have hundreds and hundreds of them, and so PDN is their abbreviation for Poincare duality property. So an example then is a fundamental group of a closed aspherical manifold, n-manifold. All its higher homotopy groups vanish. Orientable. Then gamma is PDN. And so the general question is the converse true? Well, there's a counterexample to the converse. There exists an infinitely presented group, PDN group, for n greater than or equal to 4. This is due to Davis, Mike Davis, in '98. And actually, sorry, I didn't do an exhaustive check of the literature to see if there's anything earlier, but this is what I found. But anyways, an infinitely presented group cannot be the fundamental group of a compact orientable manifold. So if the manifold is, CW complex, then that's fairly obvious. But there's a theorem, I guess, I think it was Casson and Kirby, that shows that any manifold's approximated by a CW complex. So you can, so it'll be finite. Any closed closed n manifold has finitely generated fundamental group. In 3 dimensions, we know that any 3 manifold by Moise is triangulable. So, but the question then is, actually, sorry, I think it is finitely generated. Yeah, so Davis takes examples of Besvina and Brady of finitely generated infinitely presented groups that are of finite cohomological type, and then he does a reflection trick to get in a Poincare duality group with the same property. So if gamma is finitely presented, PDN group does gamma equal pi 1 of an n manifold, a spherical n manifold. Here Mn has to satisfy these conditions, right? So that as far as I know, this is still open in general. And in 3 dimensions, then one might hope to try to prove this via some kind of analog of the geometrization conjecture. But I don't think we know how to do Ricci flow on BGs or whatever. But yeah, that's right. So there's topological manifolds that have no smooth structure, and the Borel conjecture would imply that that was a unique up to homeomorphism. So I think that's part of the question. So prove a sort of weak geometrization conjecture. So this was actually sort of the direction that 3-manifold topologists were going, pre-Hamilton and Perelman. So this conjecture is that if gamma is, well, let's say finitely presented PD3, either z squared is in gamma or gamma is word hyperbolic. So I haven't defined word hyperbolicity, but I'll discuss this in just a second. So if we had a z squared, there's a more general question about word hyperbolic groups, that whether or not they have in general a Bohm-Sog-Solitar subgroup, which would also be an obstruction to being delta hyperbolic. And we don't know of any finitely presented groups that don't have any Bohm-Sog-Solitar subgroups in yet, which are not hyperbolic. So if z squared is less than gamma, one could hope to prove that gamma splits over a z squared as an amalgamated product, or the center of gamma is non-empty. and then try to apply the proof of the Seifert space conjecture to that case. So that's one strategy that seems like plausible. So when you have a z-squared subgroup, there's this theory of generalized JSJ theory of groups that might be applicable here to prove some kind of amalgamated product. In the case that's sorry, say again?
Won't you need some analogies for Hardy-Davis boundary also if you want to make some amalgamation?
Yeah, that's right. So then you would amalgamate a product, and you would need a more general. So you're a relatively hyperbolic group that's point graduality in a relative sense. That's right. So yeah, and then you could hope to prove that inductively. Let's see. I guess I'm out of time. So maybe I'll just say a couple words about the other case. The ordered hyperbolic case, your Cayley graph sort of compactifies to a two-sphere if it's a PD3 group. That's known by results of Besvinian mess. And the action of the group on that two-sphere, you want to show its conjugate to a conformal action on the two-sphere. So that's the essentially equivalent to showing that it's a three-manifold group. And there's been some progress on this recently by Vlad Markovich. They showed that if you can find enough surface subgroups inside of there that are nice inside of the group, then you can actually prove it's a three-manifold group. So that seems like an interesting. So if you could generalize this Kahn and Markovich machinery to this context, then there's a good chance of solving it that way. But anyway, so I'll stop there. Thanks.